Right. Good day, I guess. And welcome to another session of our trigonometric function introduction. That'll span 3 sessions. You've done one already, and we're very close to the end. It might not feel like it, but we only have a few topics left. We have our basic introduction of trigonometry that we're working on now. Then we have I won't ruin it, but the extension from polygons to 3 dimensions, those shapes. That is definitely in the elementary school curriculum, so we kind of need to know some of those names. And then lastly, we're going to revisit area and volume as well. So 3 topics. But the nice thing is that we have enough time in our schedule so that we can take our time, work through them at our own pace, really, and ease into the end of the course. So, previously you have worked through our basics of trigonometry, mainly focusing on the conversion between degrees and radian measures of an angle. Now, I will admit that for our purposes, it's really just an awareness of this different better degree, no, sorry, this different better angle measurement. But it's only when things get fancier that we really need it. We are not gonna go there because this is just an introduction. So it's really just a matter of awareness. But in doing that uh, discussion, we learned things like let's make that dot the center. That's perfect. Oh, it's not perfect, it's close. In that discussion, we learned that, well, let's make the center over here in a circle. If I have a little wedge, so, and I have my radius, and I have my angle, that is a very wobbly theta. See, the pen maybe can be a little better. Spanning a circular arc from there to there. Then we saw that the relationship between these three, or really the relationship between arc length and radius, is consistent across the same angle, even though the circle can be different. Suppose that's the center, and we have the same angle, more or less. I'll label it, and then let's say R1 and S1, new radius, new arc length, but they're all the same. Arc length over radius is consistent if the angle is the same. Then both of these point to the same angle. That's the radian measure. And then we discovered pi and how to convert between degrees and radians and so on. Now, what's interesting is that if we do something similar but for triangles, we get similar consistency in the relationship between those two quantities, but of course it's not going to be arc length anymore. If I have a triangle, uh, as long as it is a right angle triangle, let's make one here and a similar one here. So I have the same angles, they're similar. Let's suppose that is whatever, theta. I do have to have, in the case of triangles, a right angle triangle. I have the same uh, angle. They're similar. which means one is just a zoomed in version of the other one. Let me just open something real quick here. Check my audio works. Now I just want to label these sides of the triangle. This is triangle 1, and this can be triangle 2. Of course, they have different side lengths. Now, relative to the angle here, this bottom left angle, this bottom edge of the triangle, I'll call A1 for adjacent. It is the one of the perpendicular sides that is touching the angle that I'm focusing on. It's adjacent to the angle. This is a new adjacent angle, adjacent side, longer, right? It's the bigger version of the triangle. So I'm going to call it A2. Then I have the other perpendicular side that is not touching this angle. It's opposite to the angle. See, it stands on the other side. We'll call it O1 and O2. Opposite. And then we have the hypotenuse. In both cases, I'll call it H1 and H2. So what they found, similar to the circles and the wedges and the arc length radius relationship, they found that for similar triangles, so let's say here, for similar triangles, meaning the theta is the same, the angles are the same. These ratios of all the combinations of fractions I could make with these three, adjacent, opposite, and hypotenuse, there's a consistency. So if, for example, I look at the opposite relative to the hypotenuse, I'll say opposite 1 over hypotenuse 1. And I compare that same ratio in the larger version, opposite 2 over hypotenuse 2, they're the same. Now, it's a little bit more general, actually, than the wedges up here, but we have similar, the idea of ratios, again, somehow being linked to the angle. That if I just zoom in on this triangle, yes, the lengths change, but the ratios don't. But because I have three things here in my triangle, three side lengths, I can make other ratios as well. I can take adjacent to hypotenuse, adjacent over hypotenuse in the first triangle, adjacent to hypotenuse in the second triangle. The lengths are all different, but the ratio turns out to be the same. And of course, I can make another zoomed in version. I could make a tinier version as long as it's similar, as long as the angle is the same. All those ratios will be the same. I just took two examples. My last combination of two of the three sides will be opposite and adjacent. So in the first triangle, opposite 1 to adjacent 1, opposite 2 to adjacent 2, they're also the same. So because I have three and I'm choosing two sides to be in a ratio at a time, I have three different sets of ratios, so to speak. Three different sets of ratios. They're always the same. So let's say here, whoopsie, corresponding ratios always, ooh, that's ugly writing. Let's try that again. Always the same. Of course, I can't go and say the opposite to hypotenuse ratio matches the adjacent to hypotenuse ratio. It's a different pair of sides. So I have to stick with the same thing. But then as long as the angle stays the same, whether it's a zoomed in triangle or a zoomed out triangle, the ratios are the same. So just like for the little wedge arc length radius relationship ratio, because they're all the same, always, regardless of the size of the triangle, if I change the triangle to have a different angle, then the ratios won't be the same as for this triangle. But because I'm zooming in and out with the same angle, the ratios are really connected to this angle. So these are all, I'm going to write it over here. These are all somehow connected, connected to the angle. Somehow. Now, when they realized this, they went and said, okay, well, let's pick an angle and measure some triangles and see what ratio we get for this first one, for example. Let's focus just on the first one. Let's pick a triangle. By picking an angle, you're essentially specifying this right angle triangle. Because now I realize, regardless of the zoom level, it's the same ratio. The answer is the same. So I pick an angle, I make my right angle triangle, I measure the side lengths, I calculate this ratio. I get whatever I get. I pick a different angle, make it a little wider maybe. Make my triangle, measure the angles, get another one, get another ratio. And so I can keep going and get these ratios, make a table, a book of numbers for these ratios that cover all the angles, because the angle directly corresponds to this ratio. Different angle, different ratio. But for a specific angle, it'll have a specific ratio. For example, let's write that out here. For example, if I make a triangle, let's make some space here. Let's make a triangle. Now, I'm not going to be able to measure it here, but if I take a 30-degree triangle, right angle triangle, whatever this is, adjacent, opposite, hypotenuse. So they make the triangle, they go and measure these angles, they find the ratio, dotted line, get away from me, ratio, opposite to hypotenuse is 1/2. Always. It doesn't matter if I make a big triangle with a 30-degree angle. It doesn't matter if I make a small triangle with a 30-degree angle. The opposite to hypotenuse side lengths will be in a 1:2 ratio. Always. Change the angle, of course this ratio is going to change. Make it a little bigger, it's going to get a little bigger, and so on. And so it changes, and they made a whole book of numbers for these ratios that you can go and look up. But because of the time that we live in, that book was essentially digitized and is now on your calculator. So to enable us to look this up, we call this ratio a function of the angle. A function is simply, let's say it over here, function is simply some calculation, some button on your calculator, some mystery box that you don't necessarily see. I give it an input. In this case, I'm going to give it the input, which is the angle. It does what it does. It looks it up in the book, whether it's digital or not, and it gives you the output, which is the ratio. Let's say here I put in 30, make it specific. I put in 30 degrees, it gives me the ratio 1/2. A function is simply this calculation. Sometimes it's an actual calculation, sometimes it's looking it up in a book, sometimes it's the calculator looking it up in the book. Either way, they could go and figure out these ratios on their own. So this function that gives me the ratio opposite to hypotenuse is called the sine function. Remember, it takes the angle as input, sine function of the angle theta. But in this case, it is a little bit more complicated because I have other ratio pairs. Excuse me. I have the adjacent to hypotenuse ratio as well. And those numbers will be different. If I measure adjacent to hypotenuse, it's not going to be a half for the 30-degree angle. And in general, they're not going to be the same. So I have three of these functions. The adjacent to hypotenuse one is called the cosine function. And of course, again, it's linked to the angle. And the last one, opposite to adjacent, is called the tangent function of the angle. So we're going to write this for short e sine, maybe in brackets. The brackets usually indicate what is the input. What should I calculate? Oh, behind the scenes, an opposite to hypotenuse ratio. Just give me the answer. Cosine is cos of the angle, and tangent is tan, and we often just say the tan function. Now these are built in to your calculator. You don't ever, unless you manually want to go and draw a triangle and measure the side lengths and calculate the ratios manually, you don't have to ever do that. So these are our trigonometric functions. You don't ever have to do that. Now, oopsie, sorry, our calculator differs, of course, from one person to the next. There's so many. I'm using MathBot as a calculator, which is also different. But regardless, be aware of where these buttons are on your calculator. And now we want to essentially first practice using them. So yes, it's interesting to know where they come from, but at a superficial level, we don't have to actually think of the detailed ratio. We just want to now practice the calculator aspect so that you can take the time and look at where these buttons are on your calculator that you're going to use so you can get used to yours. Let's make a new page here and go to our exercises. I'm going to look at exercise 15.4. Small, let's drag it, make it bigger. Check how it looks. It looks okay. 15.4. Find the following sine function values without a calculator. So let's just ignore this because I'm not ready for it. I want to just practice the sine function, of course, knowing there are others. And I just want to practice it for these two because I want to learn how to use my calculator and understand, remember that there are different measures for an angle. If I have a function that calculates my speed, for example, and I give it an input that I've traveled in kilometers versus input in miles, well, that's kind of important to use in the calculation. Just like this, if I'm giving it degrees, I need to be aware of that versus giving it the radian measure of the angle. Let's zoom it in. So I'm not doing this exercise properly. We have to just get used to the calculator first. Now, if you're using a basic scientific calculator, you want to be aware. Whoops, writing and speaking is not my strength here. for a DRG button. That's going to cycle between degrees and radians and something else we don't care about right now, or really ever for us. And it'll say in the bottom of your screen, or at the top sometimes, it'll say here, you're in degrees or you're in radians. So then when you type 30, you want to make sure if it's degrees that it says DEG, so that when you perform a calculation, it knows what measure your angle number is in. So be aware of that. In MathBot, however, it's a little different. MathBot has two separate function names for radians and degrees. I'll write it over here, just in case you see it in the chat. If I have the radian measure, the function, sorry, if I have the radian measure of an angle that I'm using, it'll just be sine, I think I have to put brackets, no, not 30, of whatever my angle is. If I'm using degrees, I have to see, well, I'm all over the place today. Sine D, telling it, oh, that's degrees. This isn't a standard name for the function, it's just in MathBot because it doesn't have the same setting as a calculator where I can change things permanently. So with that out of the way, let's practice the first one, sine 60. When things are this simple, they often in books don't have brackets around it, but be aware that there are always brackets around it. But when it's not really mixed with anything else and pretty simple to read, they often drop the brackets just for appearance sake. But it's always there. So practice along. Make sure you can find it. Let me just see if MathBot is awake. It says 3 plus 2 is 5. Good job, MathBot. Now let me see if I can remember my sine function because this angle is given in degrees. My MathBot function is sine d to tell it what measure my angle is in, what units. So sine d, I'll put a 60, 60, like that. It does its thing. We don't have to worry about that right now. Whoopsie, get bigger. And it says 0.8660. Let's use 4 decimal places. Right, so if you get 0.8660 and more digits, then you did it correctly. The next one, number 2, is sine of pi over 3. See, there isn't a little degree circle. That means it is in radians. Pi over 3, which I know is 60 degrees as well, right? It's a different unit measurement for angle. So then make sure if you're on a scientific calculator where this DRG button applies, cycle through until you see radians at the top because that is the angle measure that we will use. So I say my sine function and then pi over 3. Now in MathBot it's only sine pi over 3 and we should get the same number because it was the same angle. 0.8660. Don't want to assume that you've used your calculator in this way before, so I take my time. We have so much time, why not? But if this is too easy for you and you're watching the video after the fact, just feel free to speed it up or whatever. Sine 30. And yes, the calculator does some fancier things, but I can very much think of it as it's just looking it up in a table in its memory where all these things have been done. And long ago, the very beginning, they were written down in a book that if you ever in a calculation we'll see tomorrow have to use the sine function of 30 degrees, you go look it up and you use that number. It's the same thing here. It's just sort of digitally done, right? Sine 30. So 30 degrees, I have my degree measure. So change your settings accordingly. Let's see what it is. So for me, it's sine d. Now we already calculated it, right? Well, not calculated it. I sort of said it was a half. It is the half that we saw previously. Why is it a half? Well, we'll get to that in a second. And the fourth one, whoopsie, why do we keep minimizing the wrong thing? Book. Sine 45 degrees. 45 degrees. I'm in degrees, so want to make sure my settings are correct. A common mistake is to be in degrees when you're using radians and be in radians when you should be in degrees. That's something I want to be aware of. So I'm in degrees. So MathBot requires that I attach that D so that it knows what I am working in. And lastly, sine of pi over 4. That is a radian measure of an angle. I know the angles because we did the conversions first. Pi over 4 is 45 degrees. So I should get the same number. I'm really just practicing my calculator side so that in a test where I will use a calculator for this, in some problems, I want to be confident in that on that side. Sine of pi over 4 get, of course, the same thing that we should get. Okay, so hopefully that helped us. And I want to leave this open. I want to come back to that page in a little while. So now we can do the exact same calculations with cosine and tan, right? Same thing. Just different buttons on your calculator, perhaps, different function names because they are different functions using different pairs of these three sides. So having done that, you noticed perhaps that the question in the book was originally calculate these function values without a calculator. It gives us some insight that'll help us for our word problems. If we focus on some familiar angles, and 60 degrees, 30 degrees, 45 degrees will be our familiar angles, or their radian equivalent pi over 3, pi over 6, pi over 4, which it's best to memorize and know. If we can handle them without a calculator. We've done the calculator looked it up for us, these are the values. Where do these values come from if I don't want to round it? But I can only really do that for familiar, simple angles. 30, 60, 45 degrees will be the only ones. So these are the common angles that I want to explore a little further. And in doing that, I gain some insight and learn actually a little more than just finding sine of 60. So the first one is the 30 degree, 60 degree angles. 45 has its own procedure. So what I'm going to do is I'm going to start with an equilateral triangle. Now I'm freehanding this, so it might not look perfect. I think this is pretty close. Let's fill in the gap there. Equilateral triangle, meaning all sides are the same. That's what I start with. Okay. Now, I'm not going to write the steps for you, same as what we've seen before. Watch the video after the fact, write the steps out for yourself to get to our end result so that it makes sense to you. Okay. One thing I want to note that we have mentioned before. Sum of the interior angles of a triangle is 180 degrees. They add up to 180 degrees. Now, a property of the equilateral triangle, which is a regular polygon, is that everything is the same. All the side lengths are the same. All the interior angles are the same. Everything is as same as it can be. It's the most structured polygons. So all these angles are the same. So if there are three of them, adding up to 180 degrees, we've seen the interior angle of a regular triangle, equilateral triangle, 60 degrees. So 60 degrees, 60 degrees, 60 degrees. When we talked about tessellations, we did this. It was in our table, and we have to be able to calculate the interior angles of other larger regular polygons as well. Here, we're just interested in the triangle. Okay, so that's where we're at. Now I'm just going to erase this top one to make space. What I'm now going to do is I'm going to take from this top vertex down a perpendicular bisector to the opposite edge. Because it's regular, that is going to be, well, this top vertex is already perfectly in line with the center of this bottom line segment. So it's going to split that line segment in two and actually be a perpendicular bisector. In truth, I sort of draw it down, but because of the balanced symmetrical nature of this triangle, I split it in half. So it is, in the end, a perpendicular bisector. In this gap. There we go. So once I do that, another property is that it splits this top angle in half as well. Everything is as balanced as it can be. So now I have two little 30-degree angles. See how I've created the angles 30 degrees and 60 degrees in a triangle? I just have double the triangle. And I don't really care to see things twice, so I'm going to erase this side of it. I'm going to only do a sloppy job of erasing so that you can see, oh, it was there, but it's the exact same thing, so don't care about it. And there is my 60-degree, 30-degree triangle. Now I can check this triangle, the sum of the angles, 90 degrees, 60 degrees, 30 degrees, it's still 180 degrees, so everything is good. If I backtrack a second, there we go. I can now pick any length I want. At the very beginning, I'm going to pick a side length of 2. 2 and 2. Because it's equilateral, right? Equilateral triangle, all the same side length. Let's pick a nice number. Let's pick a 2. 2 is super nice. Now, when I do my perpendicular bisector down, I know that this side length is 1. I don't want to create fractions or weird numbers. I want to make it easy. Then when I erase this, I have a triangle that has easy side lengths to work with. I know I'm not erasing it very well, but it's done on purpose. So this triangle has side length, a hypotenuse side 2, whatever units I don't care. And this perpendicular, one of the perpendicular sides is a 1 length. Because remember, I don't care what they are, I only care about the ratio. So I can pick comfortable lengths to make my job a little easier. The problem is I don't know what this other perpendicular side length is. In comes Pythagoras. If I have a right angle triangle, let's call this A, B, and C, not to be confused with this A, though luckily it's in the same position. Pythagoras, which we've also discussed, says the sum of the squares of the perpendicular sides is equal to the square of the hypotenuse. I can use that here and say, well, this bottom perpendicular side is 1 1 squared. The upright perpendicular side is question mark squared. Maybe let's put it in a box. Doesn't drift away. And that has to equal the hypotenuse side squared, 2 squared. So I get 1 plus question mark in a box squared equals 4. So question mark in a box squared equals 4 minus 1, 3. So question mark in a box equals the square root of 3. Square root of 3. And now I know everything about this triangle. It's my 30 degree, doesn't matter if I freehand this, 60 degrees, 30 degrees, 2, 1, root 3, which I want to memorize because I want to understand where this comes from, absolutely, so that if my memory fails me, I can reconstruct this. But I don't want to do it every single time. It took a while. It took a while. So it's convenient to just memorize this one, but at the same time understand where it comes from. The beauty of this is that now I can calculate sine of 60 degrees by simply understanding what ratio it requires opposite over hypotenuse. Now, relative to this 60-degree angle, opposite is root 3. Hypotenuse is 2. Let's calculate that and see if we get our 0.866. That we did. Now, in general, I will leave it there because that's the exact version. Let's not do that. Let's just say compare to 0.8660 just by way of the calculator. And let's see, square root of 3, square root 3 divided by 2. And look, it's exactly the same. It's exactly the same as what our calculator looked up for us, which it should be, right? It should be. But now this is exact. It's not a rounded number. It's not a rounded decimal number. Because this square root of 3 is a non-terminating, non-repeating decimal number that goes on forever. But if I leave it in square root of 3 form, it's exact. So that's what they mean when they ask to find this without a calculator. Out a calculator. Okay? I can also do sine of 30 degrees. So here's where I just want to be careful if you're not used to this. The sine function always takes the ratio opposite over hypotenuse. What is hypotenuse doesn't change. What is opposite changes depending on the angle I look at. For 60 degrees, opposite was the square root of 3 side. But for 30 degrees, opposite is the 1 side. So for 30 degrees, opposite is 1 over hypotenuse is 2. 1/2. 1/2. So I have to sort of pick the correct perpendicular side relative to the angle that I'm looking at. Okay? Very important. Pick the correct side relative to the angle that I'm looking at. I just want to go and check where can I do cosine and tan and stuff now because I want to. Later, I suppose. Okay. I kind of want to do it now, but I guess not. No, let's stick to sine. It's fine, whatever. Because we have one more triangle to do. Okay, so this triangle gives me two angles, 30 degrees and 60 degrees. You can talk about it in terms of radian measure as well, pi over 6 and pi over 3, but that doesn't really matter. For just finding the function output and nothing else, not part of a larger calculation or anything, then because my calculator can handle both inputs in this simple situation, it doesn't matter which one I'm in. The other angle that is considered a common angle is 45 degrees. So let's do the 45-degree, I guess, angle. I just say the 45-degree triangle. What I'm going to do is I'm going to draw an isosceles triangle, which everyone, of course, knows what that word means, right? And it's going to be a right angle triangle where the perpendicular sides will both have length 1. So in a right angle triangle, I can't get the third one to be the same length, and I don't want to either. So I'm going to start with an isosceles triangle. The perpendicular sides have side length 1, and it is a right angle triangle so that I can use Pythagoras. Plus, the ratios only worked on right angle triangles anyway. So now the question is only, what is this hypotenuse side? Well, Pythagoras to the rescue as well. But before I do that, let's notice that let's note, for any isosceles triangle, a property that they have, that of course we didn't prove, is when those two sides are the same, the angle that they make with the other side, called the base if you will, those angles are the same. That's a property that you'd have to go prove based on those basic assumptions that Euclid made and build up from that. And it's a whole thing. To be proper about it, we can just take it as a fact. So these angles are the same. But now if we call it theta, then they have to add up to 180 degrees. So theta plus 90 degrees must equal 180 degrees. So 2 times theta equals 90 degrees because I subtracted 90 on the other side. And theta therefore is 45 degrees, which is why I call this the 45-degree triangle. Let's make this one 45. They're actually both 45. 45 degrees, 45 degrees. Okay. Okay, so the angles are done. It's the correct angle that I want. Let's just figure out this other hypotenuse side. Well, the sum of the squares of the hypotenuse the sum of the squares of the perpendicular sides equals the square of the hypotenuse. So I have square of question mark in a box. 1 plus 1 is 2. So question mark in a box equals square root of 2. Let's update that guy, square root of 2. Now, if you remember these things well, perhaps in school you had slightly different numbers. I don't care. This is the only one I need and I have ever used. There is no need to make multiple versions of this. I just pick whatever's comfortable because only the ratios matter. So then I'll just use this one. If I want, there's only one sine function I really care about here. It's the sine of 45 because they're both 45. There's no flipping of the angles. Sine is opposite. I'll just look at the bottom one. Opposite over hypotenuse. So 1 over root 2. Did we actually do that? Here, 0.7071. Let's see if we get 0.7071. 1 divided by square root of 2, 7071. Exactly the same as what the calculator looked up. All right, so we have our two triangles here. And then we can use those two triangles to calculate, just for practice, the exact versions of the other two trigonometric functions. which we haven't done. So I guess we do have it over here in exercise 5.6, 15.6 rather. 6. And for that, I need my triangles, right? I just do a rough drawing of the 60-degree, 30-degree triangle, 2, 1, root 3. And my 45-degree triangle, 1, 1, root 2. So the first one in our last few minutes, cosine 60 degrees. Cosine 60 degrees. Now I have to look at the 60-degree angle. Relative to that angle, cosine is adjacent over hypotenuse. Relative to the 60-degree angle, adjacent is 1 over hypotenuse is 2. And it's as simple as that. Yes, there's a link between sine and cosine, which is why it's called cosine. But I'm not getting into that. That gets a little mathy, and we don't really need it, to be honest. Okay, next one. So I'm just practicing reading these answers of the two triangles that I memorized. Now, in the simple case, I really just think of degrees because it's intuitive and it's easy. Pi over 3 is 60 degrees. So that's exactly it's the same angle, right? I'm not calculating it where I have to be aware of degrees and radians. I'm just looking up which angle do they want? Oh, they want the 60-degree angle. Relative to this angle, opposite is root 3, adjacent is 1. It says without a calculator, which means I don't calculate a decimal number, I don't round it, or anything like that. So be aware of what the question asks. There could be another question here, like problem 15.4, use your calculator. Then we just plug it in. But that's not what this one is about. Cosine 30 degrees. Now I look at my 30-degree angle here in this first triangle. Relative to that, adjacent is root 3. Hypotenuse doesn't change. 2. I'm going to do the others over here. Number 4, tan of 45 degrees. Tan of 45 degrees. Now I look at my 45-degree angle. Triangle. Well, angle as well. Tan, opposite over adjacent. 1 over 1. I want to write 1 over 1, though you can simplify it afterwards in this case, because I want to show how I picked the sides of the triangle. That's my work. There's not much work to show, so what little work I can show, I want to. Last one, cosine of pi over 4. Now I should know by now pi over 4 is equivalent to 45 degrees. So I'm back to my 45-degree triangle. Cosine is adjacent over hypotenuse, 1 over root 2. I literally read it off. I just have to remember these two triangles or how to make them, or a mix of the two. And then when they ask me to do it without a calculator, I literally just read it off by understanding what the trigonometric functions require in their ratios. It's just reading it off. I don't even do anything with that answer. I leave it exactly like this. All right, so that gets us a little bit further. And these trigonometric functions we are going to need when we get to the word problems. There's a couple of word problems, 15.5, 7, and 8, that we will do next time. In the meantime, there is some problems you can practice. 15.1 is a conversion problem, which you might have done already. 15.2 is a conversion problem in the other direction. Problem 15.3 is ones we sort of just did. Find the cosine, sine, and tangent of these angles. And then you can also practice your calculator use, which is important, in 15.4. 15.5 is also a problem that you can do, but don't skip the other ones. Build up to it. They're in a good arrangement here. where we want to practice Pythagoras and some of the angles being 90 degrees to see if we can find the missing things in these triangles. And maybe we'll start with one of these tomorrow because it's often one that we don't have a specific working example yet to compare to. So we'll start with one of these tomorrow, I think. But you have enough to do in the meantime. All right. Are there any questions about any of this that you would like to share with everyone? Right? Then we will continue this next time. Until